Hello and welcome to the course whose title is Application of Symmetry and Group Theory in Chemistry. This is the first day of this lecture and I welcome you all to this course. Let's start with the introduction of this topic as a whole. So this particular topic, symmetry and group theory, this is of utmost importance for chemists, particularly any form of chemistry like inorganic chemistry, organic chemistry, physical chemistry, and also to the audience belonging to chemical engineering and even physicists. In chemistry particularly, say an inorganic chemist who all the time talks about, say, bonding in case of transition metal complexes. Okay, so in transition metal complexes, people talk about formation of linear combination of atomic orbitals to form so-called symmetry adapted linear combination. So many of you are probably familiar with this term, symmetry adapted linear combinations, or in short SALC. Now, how this linear combination is formed? Okay, there are certain rules which are based on symmetry. So that's why it is called symmetry adapted linear combination. So one needs to know what is the relation between this symmetry of any given molecule and the formation of this molecular orbitals. Similarly, a spectroscopist or a physical chemist who wants to know about the possibility of a transition from one given energy state of the molecule to another electronic state. So there, knowing the symmetry of the states, or in particular the symmetry of the wave functions related to those electronic energy levels or vibrational energy levels is very much needed. Okay. So in various aspects we will need this molecular symmetry. The symmetry, when we say molecular symmetry, what I mean is the symmetry of the molecular structure in general, and in particular symmetry of the wave functions of molecular electronic states or vibrational states and so on. Now when we talk about symmetry, what comes to our mind first? So let's have a look at the result that we obtain by putting the term symmetry in a Google page. Okay, so here it is. You can see there a definition of symmetry is given here, which says like the quality of being made up of exactly similar parts facing each other or around an axis. Okay, so which also tells you that if I can highlight that portion, so this is the definition that is given by a search in Google, and there are so many synonyms that are provided like regularity, uniformity, evenness, or equilibrium, consistency, orderliness. So all these things gives us some picture about the symmetry of an object, symmetry of a molecular structure and all. Okay, so suppose I give you a molecular structure or any object at a place. So like I give you this one, okay, the mouse, and I ask you, what do you think about its symmetry? What will be your answer? Probably you will tell, well, it is to some extent symmetry. So let's have a look at certain objects and try to see if we can say something about their symmetric. At least are they symmetric to us, or do they seem to be symmetric, or we don't find any symmetry in those structures, or we can say like, okay, this is more symmetric than other. Okay, so here is a famous picture Many of you will probably know this is a drawing by the great Leonardo da Vinci. This is the Virtuous Man. So, this is a description of a human body at two different orientations. Now, looking at this, what you can say about the symmetry of this human body? The obvious answer will be, well, this is very much symmetric. We have been reading about it in even in our biology courses. Okay, the human body or animal bodies, they are symmetric. Okay. Okay, so let's have a look at some of the other structure that we can think of. You obviously know this one is famous symbol of in the Batman movies, right? This is a picture of a bat, seemingly. So, looking at this, you can say, okay, there is some sort of symmetry. You can say that, okay. Why? Because if you look at the object in this fashion, where you look at this part, the right side part, and the left side part of this object about this line, then you can say that those two halves are almost like a mirrored image, not almost like, it's a mirrored image of each other. So, you can say this is a symmetry, okay, a symmetric object. So, similarly, if I look at another picture, let me erase those things. Okay. So, here also this is a picture of a bird, a beautiful bird here, and you can see that about the the mid portion of this bird's body, you can see is pretty much like a mirrored image. Both the sides, the wings and the tails, you can just dissect it in the two equal halves. So, to you it will be like a very symmetric object. Now, here comes one of the 7 wonders of the world is the great Taj Mahal. So, looking at this phenomenal architecture, you can at first say it's very, very symmetric, and your observation is very true, particularly when you look at from a top view, that is an aerial view of Taj Mahal. You can see how nicely this architecture was built. So, look at, there are 4 domes, one here, one here, one here, one here, the doors here. So, you will find the same pattern of doors on each side of this Taj Mahal. So, if you start from say one dome and go through the center part, you will reach the other dome. Similarly, here if you come through this center of the Taj Mahal, you can reach the other dome, fine. And if you are standing, suppose near this dome, and look at Taj Mahal, and then you go all the way to here and stand here and look at the Taj Mahal, you will not find any difference between your views. Okay. So, that is why this is symmetry. And when I say go back and say like, okay, I showed you the picture of that bird, and now I am showing you this picture of Taj Mahal, you will probably say, well, to me Taj Mahal seems to be more symmetric than the bird. So, let's look at some of the other structures that we can that we see almost every other time. This is a famous lotus example, lotus temple, sorry. This is also a very, very symmetric. Okay. So, you can easily say that it's very symmetric structure. So, now, let us look at some of the other structures. Here it also looks pretty symmetric. Here it is the a building, famous building, many of you know, this is called Pentagon. It's the it's probably the head office of US Defense. Now, this is also highly symmetric. Okay. Now, when we say this, that okay, this is very symmetric and one is probably more symmetric than others, then how do we say that? How can we say one structure is more symmetric than the other structure? We will know how to do that. Okay. Now we have seen some structures which we can say that okay, all of them are to some extent symmetric. Some are more symmetric, some are less symmetric, but overall symmetric. Now let's have a look at this, and how does it look? Does it look symmetric to you? This is a picture of tree which has like an arbitrary shape. Okay. So if I ask you whether it is symmetric or not, you will say there is no symmetry. So you can feel intuitively whether a structure is symmetric or not. Okay. So far all of us, we have developed some sort of intuition so that we can say it is symmetric or not. Let's have a look at some of the other structures. Facebook symbol. Okay. If I ask you, you will say it's not symmetric, because when we looked at the symmetric structures, we could start from one particular point and go to another direction, and ultimately we will find almost equivalent point at the other side. Here we don't have something like that. Okay. So no two points in this particular Facebook has the same environment, this Facebook logo. So we can call this, and this is not symmetric. Now same is here, it's a zigzag railway track. I don't find any symmetry here. The oldest bicycle with a bell, I don't see any symmetry here as such. It's a building, amazing, but doesn't look symmetric. A famous classic example of a building which is known as Burj Khalifa. Many of you have probably seen the picture of this. Now apparently it looks symmetric, but a close look at this building will tell you that this is not symmetry, which will be obvious if I tell you. See, if I can mark these places, so there is a central line through this one, and then if it is symmetric, then both the sides should be equivalent, right? So if I look at a part of the building here and here, they are not same. Their heights are different. Same thing is here and here, here and here, here and here, all through. So this is not actually symmetric, though apparently it looks like symmetry. Okay. So the thing that I want to convey to you, that by looking at the structures we can say whether they are symmetric or not. So now so far we have been talking about the symmetry of objects like buildings or creatures, architectures. Now ultimately we are going to deal with the symmetry of molecular systems, right? So let's have a look at certain molecular structures, and then let's see if we can comment about their symmetries. Okay. So let's have a look at a molecule called phenylalanine. So this is phenylalanine, it's an amino acid. Now for a second you forget this part. So this benzene moiety, just only the benzene, if you look at, it's very much symmetric to you, right? Okay. So any point on this object can find an equivalent point on the other side of the molecule. But as a whole, when I talk about this phenylalanine, I have a molecular structure where you have this amine group projecting outside the plane of the molecule, and this C double bond O or OH, they are in the plane of the molecule. So overall it doesn't seem to be a symmetric molecule, okay, which is obvious. Now similar is here for a molecule tryptophan. I don't see any symmetry in this molecular structure. Ascorbic acid tells me the same thing about its structure. Cysteine, another amino acid, all are not having something which can tell me that the molecule is symmetric. Okay. Now let's have a look at these molecules, the most common molecule on earth, so water. This is the structure of water, oxygen and two hydrogens are bonded. Now suppose I can somehow mark. Okay, so before that, I mean, if I look at this molecule, it seems to be somewhat symmetric to me. How? Let's try to explain that. Suppose I can mark this hydrogen atoms somehow. Okay, so I mark this hydrogen as 1 and this hydrogen as 2. Okay, and then so this water molecule is like this, correct? So one hydrogen here, another hydrogen here, and the oxygen is sitting here. Now, if I interchange this 1 and 2 by some way, say for example, I do it like this. If these hydrogens are not marked 1 and 2, I have no way to figure out whether there is anything, any change that has happened to this molecule. So, in other way, I can say that if I simply take this water molecule and then rotate by 180 degree, and if the hydrogens are not marked by numbers 1 and 2, then I have no way to figure out that there is any difference. So, they are essentially indistinguishable. Okay. So, this is the term that we will be using many times, that after doing this 180 degree rotation, I get an indistinguishable molecular structure. Okay. So, this molecule is symmetric definitely, because I can interchange 2 hydrogens and get an indistinguishable structure. So, we are slightly heading toward some sort of quantification. We will come to that. Let us have a look at another molecule which is also very much known to us, particularly the students who have been working in chemistry laboratory, organic or inorganic or even physical laboratory. We know about ammonia. So, ammonia has a pyramidal structure, as you can see here. So, 1 nitrogen and then 3 hydrogens are like occupying 3 vertices of a triangle. Like if I can draw right here, so if I mark this place, this hydrogen atom as 1, this hydrogen atom as 2 and this hydrogen atom as 3, and add 1, 2 and 3 by straight lines, I will find something like this, an equilateral triangle, where this nitrogen is sitting somewhere at the center above the plane. Fine. So, now I have marked these hydrogens as 1, 2 and 3. So, let us mark them 1, 2 and 3. Now, suppose I give a rotation about an axis which passes through the nitrogen atom, and say I give a rotation of 60 degree, I give a rotation by 120 degrees, okay, like in this way. So, about this axis I give a rotation of 120 degrees. So, what will happen? This I will get again a triangle, because this is an equilateral triangle. Any rotation about this center of mass or center point, if I give a 120 degree rotation, then I will get again an equilateral triangle. So, here if I give a rotation which is clockwise, then what will happen? This 1 earlier which was in the top, it will come now here, 2 will go here and 3 will come here. Now, if I hadn't have marked these hydrogen atoms, then I would have no option to figure out whether anyone has done anything with this atom. But actually you can take this atom and rotate it, suppose. So, I can get several indistinguishable structures of these molecules. Okay. And if I ask you at this moment, you have seen water structure and now you are seeing the structure of ammonia. And we said water was symmetric, ammonia is also symmetric. Which one is more symmetric? The obvious answer will be ammonia. Okay. Probably we have started developing that, okay, if by some means we can get more number of indistinguishable structures for a molecule than the other, then the second molecule will be more symmetric. Okay, we will try to be more quantitative. Okay, so now we have a benzene in our picture. So undoubtedly anyone will say this is highly symmetric. That is what exactly one will use, the term highly symmetric, and this is way more symmetric than ammonia and obviously than water. So another molecule, methane, this one is also very symmetric. Now we will try to find out how we can say that one particular molecular structure is more symmetric than other. Okay. So as I said already that you can have an intuition, okay, by which you can say that okay, this is symmetric and this is more symmetric than the other, but how you can be bit more quantitative in that sense? Can you use some mathematical tool or mathematical way to say okay, exactly this particular molecule is more symmetric than this one? Okay. So that is what we will try to do now. So that is done by some concept of symmetry elements and symmetry operations in the molecule, and at the end we use these symmetry elements and symmetry operations to form a mathematical group, and this mathematical group is utilized to quantify the symmetry aspects of any molecule, molecular electronic states, its wave functions and so on, and which we will be using throughout this course. Okay. So we have this two things, symmetry elements and symmetry operations. So let us first worry about symmetry operations. Okay. So what is a symmetry operation? Okay. So let's, what is a symmetry operation? That's our question. So symmetry operation is a movement, okay, by which any object can go from one configuration to an equivalent or identical even configuration. So when I say this equivalent, I can for sure use the term that under this movement the object goes from a particular configuration to another indistinguishable conformation. So say for example, if I have an equilateral triangle, okay, and I can imagine that okay, there is an axis about this. So the axis is toward you, the axis is out of the plane of the board. So if I give a rotation about this, so suppose I give a rotation like this by 120 degree, just like we showed earlier, I get another equilateral triangle, and these two are indistinguishable. Okay. Do not go by my drawing, that will give you a different size, but assume that these two are equilateral triangle of same size. Okay. So these two are indistinguishable. Okay. So we say indistinguishable structure. If I could mark, then I could write like this 2, 3. So upon a 120 degree rotation, this will come here. So 1 comes here and 2 goes here, and obviously 3 comes here. So these two, when I mark them, I can say that they are indistinguishable, okay, but they are not identical. Okay. Now if I give one more such rotation So then in that case 2 will come here, 1 will go here, 3 will go here. Okay. So I have a configuration like 1 comes here, 3 goes here, 2 comes here, and another such rotation will give me a structure for which 1 is going here. So this is 1, 2 comes here, 3 is here. Now you look at this, the relation between this and this, they are identical. So by doing something, by moving this body about this axis by a certain angle, that is 120 degree, I get an indistinguishable structure. Another rotation by the same amount of angle, I get another indistinguishable, and then another rotation will give me back the identical structure. Okay. So these movements by which I can get the, indistinguishable structures or even the identical structures are called symmetry operations. Okay. So symmetry operations, it can be explained in another way also. That is, suppose I am looking at some object, okay, and then for a moment I turn around, I am not looking at the object. Now someone comes and does something, goes away, and I turn back again looking at the object. I can't figure out whether there is any change made on that object. Then what the person did when I was looking back is an symmetry operation. Okay. Now that is about symmetry operations. Now then what is a symmetry element? So next question will be, what is a symmetry element? Okay. Symmetry element is some entity within the body. It can be an axis, it can be a point, it can be a plane. So this axis or plane or point about which a symmetry operation takes place and we get an indistinguishable structure is known as symmetry element. Okay. So symmetry operations are done about that symmetry element. So you can figure out that here we were giving a rotation about this axis, okay, the axis which is toward you. So about this axis I am doing a symmetry operation which is called rotation, and this is called, this axis is called an symmetry element as rotational axis. Okay. We will talk about that in detail in the following classes. Alright. So you can figure out that symmetry operation and symmetry elements are very much interdependent. I mean sometimes this can become a bit confusing. So you cannot have a symmetry operation without having the symmetry elements, and symmetry operations can be performed only when you have symmetry elements. So when we try to tell that any particular object, or in case of molecules, one particular molecule has more symmetry than another molecule, then what we do is we look at the symmetry operations and symmetry elements of the molecules. Okay. So if some molecule has more number of symmetry elements and symmetry operations, then obviously that object is called a more symmetric than an object which has less number of symmetry elements and symmetry operations. So if you just think about the structures that we showed, that is benzene, ammonia and water. Now if you think about those structures, then the conclusion based on whatever you have heard till now in this class is that benzene, which appears to be more symmetric, must have more number of symmetry elements or more number of symmetry operations than ammonia, which in turn will have more number of symmetry elements, symmetry operations than water. Okay. So, in the following class, we will know more about the specific symmetry elements and symmetry operations, how to find them out, and later on we will try to club them in something called point group. Okay. So, we will see again in the next class. Till then, have a good day.